Good morning, everyone. Can you hear me? Yeah? So thanks for coming on a Sunday morning at 9 a.m. I really appreciate. So my talk is about learning programming and science with scientific Python. I should have written, actually, how I learned programming and science with scientific Python, because it's kind of a personal journey. I will start with a big thank you to the organizers of the conference. So big thank you from the Scikit family, because thanks to the childcare that you provide, we were able to come as a family. So you can see the rest of the family over there. So there's a scikit-learn guy, scikit-image girl, and the scikit baby. And I have to say, it really makes a difference when you have to decide whether you go to a conference and you don't have to choose between spending time with your family and learning cool things with cool people about PyData. So I hope this kind of initiatives will continue and that other conferences will also have childcare. So let's have a big round of applause for the organizers who make that possible. So as Marco already introduced me, I am a researcher, so working in material science. I study glass. I like to do experiments in big X-ray facilities, synchrotrons. I'm also a team manager. I'm the director of a lab with about 25 people, so you see this smiling team here. And on my spare time, I'm a core developer of the scikit-image image processing package. And here is the synchrotron where I like to do experiments. So it's a big experiment with lots of cables. So you feel you're doing really science when you go there. And what I like to do is look at materials from the inside to understand, for example, if we can save energy when we melt glass at very high temperature. So here you have a movie with the raw materials of glass, so sand and carbonates. And I try to understand from this quite complicated 3D images the reactions, the chemical reactions, and if we can improve industrial processes. So this is basically my research. And it requires to interpret, to segment, to analyze these images, which are full of artifacts, which are really large too. And so the kind of problems that I have are manifold. First, I have scientific and development problems. I need to find a series of image processing operations that will allow me to extract the scientific information I'm interested in. I also need to run these operations on very large data sets. I'm talking about several terabytes of data for one experiment because it's 3D imaging, tomography, and hopefully in reasonable time. And of course, as a developer, I want scikit-image to thrive. I want it to be rid of bugs, etc. So these are my really technical problems, but I also have other problems that are sometimes more challenging, which are related to social and learning problems. Because in my team, I'm working with quite junior people who arrive in the lab and they have little experience in programming and image processing. And so I need to help them to learn both sides of the problem, programming and image processing. And of course, I'm also interested in having more developers and users of scikit-image. So this is this second part which I'm going to focus on during my talk. That is how our tools are great in order to empower people to learn fast. What is specific in our tools which make learning easy? And of course, what could be also improved? So I'll start with a little introduction to scikit-image, what can be done with it. And then I move on to this learning part, starting with simplicity, the API, and then focusing a lot of documentation and how can we make documentation more interactive. And if I have time, I'll end with a few challenges for the future. what is image processing? The definition is a bit fuzzy. It's really manifold, but you can summarize it as the manipulations of images to transform other images for other purposes. Like you want it to look better, you want to enhance contrast, and so on, and you want to extract information from these images. In science, you want to do that quite often. And so here I have put a few common tasks that you want to do with image processing. For example, filtering low contrast noisy images, feature extraction for further machine learning, segmentation of some regions so you want to label the pixels to extract objects. And when you have extracted objects, usually you want to measure things on these objects to do some science. So in this crowd, when you come to a very nice conference like PyData and you hear all these talks about deep learning, machine learning, and especially deep learning, you might think, is there a future to traditional image processing? Because isn't deep learning the universal solution to all image processing problems? And indeed, a lot of image processing tasks can be done and are done using deep learning. I have put two examples here. Image classification, that this image was taken from the Keras blogs, where you want to identify all the cats' pictures. So I have a slide with cats' picture. And also image segmentation. For example, here you want to label pixels belonging to the person and to the background. And this was done with fully convolutional networks. So you can do this quite efficiently with deep learning. So do you really need this sequence of filtering, extraction, segmentation, and so on that you do in traditional image processing? I think there is room for other tools than deep learning in the field of image processing. One reason is that a lot of people have images that are not natural images. Here is an example from biology, where you have cells that have a specific configuration, and you will not have a very large database that you can use as a learning set. And it's the same for this image that comes from a simulation, so it's not even an image that was taken with a sensor. It's a result, it's an end grid with some scalars on it. And here is another example from a colleague from my lab. She gave it to me yesterday, and so she wants to extract all these little grains. And these images are quite specific. So it's quite hard to say, oh, I will take this very big training set and do the deep learning on it. Another reason to use traditional image processing is to avoid what I would call the sledgehammer approach, because sometimes you want to do simple operations like contrast enhancement, histogram equalization. When we look at the papers which cite our scikit-image paper, sometimes they just use one function in the paper, in the scikit, and so sometimes you need to do very simple things, and deep learning is, of course, quite costly. And traditional image processing can also be used as a pre-processing for machine learning. I will have a few examples about this. So what is scikit-image? In a few words, so who here has already used scikit-image, just to have an idea? Okay. So who didn't know about the package before coming here? Yeah? Cool. Okay, great. So it's an open source image processing library. So it's not an application. It's really a library that you can import in your own packages. It's for Python, works brilliantly with NumPy arrays. And it works for 2D but 3D images as well, which is a specificity of scikit-image. Other tools work only for 2D images. And we strive to have a simple API and quite a gentle learning curve. I will insist on this point. Here are some examples of what scikit-image can do. For segmentation here, so segmentation is the labeling of pixels belonging to different kinds of objects. And for a given task, we usually have a variety of functions that do different things. So depending on your application, your image, you can choose one of them. For example, here segmentation based on thresholding, superpixels segmentation, which is an automatic segmentation, region growth with a watershed, or contour-based segmentation. So it's a bit like a cookbook. You have all your ingredients, and after you need to mix them together. Here in the PyData conference, you might be interested in the possibilities for extracting features out of images. So features can be points of interest in images, like corners, for example, or you can also extract texture feature, like Gable filter kernels, and so on. And I have an example here from my research where I have this, so it's a gypsum grain, it's what you use in plasterboards, and we're looking at the reaction, dehydration reaction, where here you have a dehydration front, and I wanted to segment the reacted and non-reacted part. So I just use these pixels and these pixels as a training set, computing DAISY features from the feature submodule of scikit-image. And after, I use this random forest classifier of scikit-learn. So you have to know that scikit-image and scikit-learn interact really well together because they both use NumPy arrays. And I used the probability vector of the classifier as an image to segment. So going back to image processing using some filtering of this probability map because it had some holes, thresholding, and mathematical morphology. So I'm not giving many details about the approach. It's just to illustrate that scikit-image and scikit-learn work really well together, and that you can use machine learning to do image segmentation here. So the package is quite popular now. When we look at the visit statistics on the scikit-image.org website, we have more than 20,000 unique visitors per month. And if we look at the typical users, it's interesting to see that maybe typical users are not the same as a typical PyData attendee. For example, I'm not sure that there are 54% of Windows computers here. I have nothing against Windows, it's just that the statistics might be different here. And also, when you look at the typical time of a visit, it's quite short. So it means that people are looking for information, but they might not find it immediately, and so they leave the website. And so half of the visits are very short. So the take-home message here is that the typical users are not hardcore geeks. They need to learn things, and they don't have a lot of time to spend reading documentation. And of course, learning and finding information is hard for them. So that's for users. For developers, we have a core team of about 10 people, and so this is quite a busy graph, but it represents the percentage of commit rate normalized by the largest contributor, and it decreases with the number of committers. So in order to understand this graph, you have to understand that, for example, this person contributed 40% as much of pull requests as of commits as the largest contributor. So the largest, the faster the decay, the less contributors, core contributors you have, let's say. And I'm glad that you seem to have understood it because it's a busy graph. And so scikit-image is here in light blue, scikit-learn here. So you see that scikit-learn has a very healthy development curve according to this graph. And scikit-image, it's quite good. So that's why I say that we have between 5 and 10 core contributors. But it's always a lot of effort to include new people and to make them confident enough to become first contributors and then maintainers if possible. So I will now start with the focus of my talk. How can we empower people and make sure that they learn fast? Because as we saw, there are some developers, but not a lot, and a lot of users, a lot of them being beginners. So we want them to learn things fast. And one first thing to do is resisting complexity. As a developer, it's very tempting often to build very beautiful cathedrals and things which can be quite complicated and will confuse your users. So how can we avoid confusing users? I'll start with this quote from the regretted Peter Hinton's, good software solves useful problems in a simple way. And I think this in a simple way is very important. And I would like to go back 15 years ago when I first started programming, just to share with you what I thought at the moment when I started programming. Programming really it felt like magic for me, because I was working with a postdoc in a lab, in a hydrodynamics lab, and he was giving me some MATLAB commands, and so they were really like magical spells. I didn't know if I had to execute all of them in the same order, if the order would change something. I had never had any programming class, and it felt really difficult because it was just some magics. And of course, you might think, okay, why are you talking about learning to program? Now most people have classes about programming. Here in this room, we all know how to program. Okay, but if we try to take a beginner's shoes, then we can understand better why it is difficult to learn new abstractions. Because mastering new abstractions is really what increases the cognitive load when you're learning things. So for a Python beginner, here are some abstractions that she needs to master. What is a variable? What is a pass? What is assigning a variable? Control flow, what is that? A for loop? Okay, I might understand it, but it's still an abstraction to master. And now when you go to data scientists who have more experience, they also have abstractions to master, like what is an estimator, what is segmentation, what is a structuring element in mathematical morphology, and so on. And if we can reduce the number of abstractions that we impose on the user, then the learning curve will be much faster. So one way of reducing the number of abstractions is to share some abstractions between tools. And fortunately for this, we have the NumPy array, which is a great shared abstraction for numerical arrays. And of course, we all know NumPy arrays. But when I started programming, actually, we didn't have yet NumPy. We had numeric. And so there were several tools which could be used. And so NumPy is great because it has a lot of features. For example, very powerful indexing, slicing, but it's also very simple. And that's why it's a really good abstraction to use for an image, because if you have a 2D NumPy array, it can be considered as an image, pixels being just array elements. So here is an example of a black and white array, and if you want to have a color image, then you just need 3 color channels for RGB. And that's the same for a 3D image. Like my tomography images, you can have a 3D array. And so using this NumPy arrays, scikit-image works with NumPy arrays both as arguments, like for this Gaussian filter here, and as output. Here my filtered array is a NumPy array. So scikit-image is meant to work very transparently with NumPy arrays. It didn't used to be this way, because when we started scikit-image, when you ask for the type of the output of a scikit-image function, then it was an image object. So at this moment, we thought, yeah, our objects are images, so it makes sense to call them an image class. And so it's really great. People will know that it is an image, and we also can have some specific attributes, like maybe the name of the file of the image or the dimensions and so on. Turns out it was really confusing users because, for example, when we asked for the max of something that was just an array, it was not a scalar, it was also an image object. So it really made users confused, and so we just ditched it, and now we have NumPy arrays. And so people just need to know that images are NumPy arrays. One thing that makes the API quite simple is also that it's the same API for both 2D and 3D images. So here you have an example of the label function labeling connected components both on a 2D and a 3D image. It's exactly the same syntax, makes things easier. And we enabled this using some little tricks, like using the np.atleast3d function, so that you can manipulate transparently 2D images as if they were 3D images. So it makes also the code base really easier and simpler. So as you see on the signature here of this quick shift filter, one filter is just one function, and the first argument is usually, it's always an image in scikit-image, and then you have keyword arguments for parameter tuning. And we have such signatures in a very consistent way, which also makes things easier for users. So the API of scikit-image is that we have submodules, and inside the submodules, mostly functions which take NumPy arrays as input, and output is also NumPy arrays. So we had a lot of discussions whether we should have submodules or not, for example. Some developers were in favor of having all the functions under the big umbrella of scikit-image. It was quite a controversy, but the reason why we chose submodules is that if you're looking for a specific function and you know what it should do, it might be easier to look, for example, for denoising filter in restoration or for segmentation algorithms in segmentation. We have mostly functions, but we still have one or two classes. For example, here's this minimum cost pass function, which is mostly used internally for other functions, but we also expose it in the API. And actually, when I looked at the website statistics, this page is almost never visited, meaning that people really prefer using the functions. And just a few words about object-oriented programming. From time to time, I have a colleague popping in my office and saying, oh, I have this new way of processing my images. I think I will make a class. And I say, stop. Do you really need to make a class? Because object-oriented programming is really okay for abstractions that are easy. Like when you look at examples on the web of object-oriented programming, you have a lot of them using a person class. And, well, a person is usually an abstraction that you're familiar to. At least you should be. And other abstractions are like geometrical objects, like points, something that you learned at school, so that it's really abstraction that you share. But a minimum cost pass, you don't really know what it is from the first start in terms of mathematics. So do you really need to make it a class? It's not obvious. Of course, I'm not saying that object-oriented programming is not good. Because when you have a very simple and consistent API, like what scikit-learn does, where you have these estimators who all have this fit and this predict methods, then the cognitive load is not high. Because it's very consistent, and consistency is very important. About consistency, we make a lot of efforts to have consistent names, and it has, so in scikit-image, it has evolved with time because, for example, now all our denoising filters are called denoise something, and also if you look at the signature of functions, then we try to have the same name for the same kind of things, like the first argument will be called image, and keyword arguments will have the same name if it's roughly the same concept, like structuring elements LM. And we also try to be consistent in the internals of scikit-image, so more for developers, for the code. Like we had a lot of discussions on the GitHub, whether we should use indices for dimensions, IJK, XYZ, or plain row column. That's what we chose at the end of the day, because it's what you can understand easily. So a lot of things are great, I would say, with scikit-image, but it's also good to learn by mistakes, to know what you do which isn't great. And I have an example of quite confusing behavior that we have in scikit-image, and it's related to data range and data type, because in scikit-image, all the functions suppose that if you have integers images, for example, for uint8, it's between 0 and 255. But if you have float images, you also have a fixed data range, which is between 0 and 1. And there are some reasons behind this choice. For example, choosing default parameters of algorithms so that they will behave well with if your image maximum is always the same. But it can be quite confusing for users. For example, when you have an image, and so it's a float image, and you compute its histogram, then you do a median filter, which transforms it into an integer image. Then when you plot the two histograms, one will be between 0 and 255, and the other one will be between 0 and 1. So it's impossible to compare what happened to the image when filtering. So this is very confusing, and in fact, a lot of our issues on the GitHub are related to this kind of magics that we do with data types. And at the moment, it's hard to change because changing this behavior would break a lot of things. But then maybe we should have asked ourselves, is really image maximum a useful abstraction or useful enough so that we impose a lot of things on our users? So that's one example where we didn't go for the simpler option, which would have been imposing nothing, and we pay it at a quite high price. So that was for the API. Now I would like to speak about really the learning process and the documentation and the teaching part, because of course we all have this romantic image of learning where we have a great teacher who is teaching great things and we just learn, but we know that when we're learning things, we are in a hurry, we don't have time, and we don't have time to go to classes. Maybe we have the great PyData tutorials, but we cannot attend all kinds of tutorials, so we need other ways to learn things. And a great way to learn things is, of course, to have good documentation, and good documentation starts with documenting the API of a package. And once again, going backwards in time, you have to know that docstrings were in a sorry state 10 years ago, because, of course, NumPy and SciPy already existed. And this was the docstring, so one line. So it was difficult to learn a lot from such docstrings. And, of course, you all know that docstrings are much better now because parameters and the type are described. There are suggestions of other functions. You have meaningful and simple examples to kickstart you so that you could start easily working with the function. So what happened between 2008 and now? At the moment, we didn't have GitHub, and it was difficult for people to contribute some help. So there was something called the NumPy Documentation Marathon, with a tool which was more or less a wiki, like Wikipedia, where you could just edit the documentation. And it was how I started contributed to the ecosystem, because at the moment I didn't feel very comfortable programming. I was not a hardcore geek, and documentation was really an easy way to get started giving back to the ecosystem. And the NumPy documentation standard was also introduced at the time. So having standards is very important, and that's why if you start a new package, you should really try to use the NumPy documentation standard. And it had a lot of impact on the NumPy and SciPy ecosystem. Of course, the documentation got better, but it also increased the standard for other packages, and most importantly, it made people proud about their docs. And I think a lot of people became contributors also because they were proud about these tools, and they could speak about it with their colleagues without them telling them, but it's complicated to use, documentation is not good. So it's also good to have more contributors. So documenting the API is absolutely paramount. You need to do that, but of course you will not read all the doc strings of all functions. You need other things, and one very useful thing is a graphical galleries of examples. So I think most of you know the Matplotlib or scikit-learn graphical galleries, where at a glance you can see different operations and click on it and have the code. And it's a bit like a menu in a Chinese restaurant where you can choose. Everything looks really appealing, and so you want to try everything. That's what an example gallery should look like. And we also have one in scikit-image, so that if you click on one of the thumbnails, you have some explanations and the code which generated it. And there is actually an umbrella project for all these galleries. So if you start a new project, you don't have to recode your gallery yourself. So who here knows about Sphinx Gallery? A few people, but not many. So you might want to check it out and use it for your own package, because now it's very easy to have a beautiful gallery from just a few Python scripts, and it will look great. So features about Sphinx Gallery. So you have the gallery, but you can also generate like small galleries in the API. So when you look at the documentation of one function, you will have the examples using this function. So it introduces links between parts of the documentation, which is very important because people will just follow one path inside the documentation, but sometimes they get stuck, so they need more link to other parts of the documentation. And there are some links also back to the API in the gallery examples. So trying to introduce a lot of links between parts of the documentation. So galleries are great, but once again, you don't want to look at all the examples of the gallery when you have a specific problem. And I don't know about you, but for me, I learn really faster when I have very specific problem which I don't know how to solve. So it's really a problem-driven way of learning. And most of you must know the machine learning flowchart, which was done, I think, by Andy Muller. So it's a bit like a game book. I don't know if you know game books, where you have decisions to make depending on your problem, the kind of data, how many features, and so on. And I think this is very useful because it's something that you can adapt to your specific kind of problem. So I think we should have more flowcharts like this. And my dream would, of course, to have something which wouldn't be a PDF, but something more interactive, where you could have your image and then these questions would be asked, I don't know, by the Jupyter Notebook or something like that. So really an interactive way of learning. So we have made some steps, tiny steps, but it's still important in this direction. For example, we have this try all threshold function, where you give your image and the output is a series of images with results from a lot of different filters. So you can choose the best for your application. So it's a way of learning first that all these filters exist and comparing the difference for your own images. So this is also something that we should develop more in scikit-image. So for a bit of science fiction, I think that gamifying learning is a really powerful way of helping people to learn fast. And I'm using this. Do you know what Duolingo is for learning languages? So it's a quite funny app which is asking you quizzes. Some quizzes are very simple and it's a bit addictive. So you want to do more, and sometimes it's more difficult. And you can just try to make sentences by just clicking on words, and you don't really realize that you're learning. It's like you're playing. So it's a really powerful way of learning. And I don't know if we could have this for NumPy, for example, just having people just clicking on words to make good NumPy instructions while they were commuting in a tube or something like that. So I'm not sure it would be as popular as Duolingo, but it might be something worth trying. And we could also do this for more complicated, high-level stuff like image processing. For example, image processing is often composed of pipelines of different operations. Like here, for segmenting this very noisy image, I had to do first a denoising step, and then choosing markers from histograms, and then using a region propagation segmentation algorithm. So could we have something where we can just combine graphically in a game different image processing operations and see the result? And it would be the image processing game, and people would learn how to do image processing. I don't know, but once again, why not try? Towards more interactivity, I think we are already lucky to work in a very interactive environment. We have IPython, we have Jupyter, which are very easy to use and have a lot of interactivity. Like we can do profiling, we can do debugging, and but there are some goodies which can make learning even more interactive. For example, Binder. Do you say Binder or Binder? Binder. Binder. Thank you. Which can turn a link into an interactive notebook, so you don't even need to have Jupyter installed on your notebook. So you can convince a colleague, for example, very easily, and to use Python. And here is the link to the very big collection of scikit-image tutorials that you can just run on Binder. And it's now possible to use Binder for gallery examples using Sphinx Gallery, so going back to Sphinx Gallery. So we don't have it yet in scikit-image, but this is an example from the Sphinx Gallery website where you have this launch Binder badge, and the example will run then in the Jupyter Notebook on Binder. So very easy way to interact with the gallery example. It takes a bit of time because obviously Binder needs to start the container and so on, but it's 20 seconds or less, so it's still very good. For more interaction and learning fast, we can also use widgets, IPyWidgets. So for example, in scikit-image, we just have functions. We don't have any graphical interface, or we have a viewer, but it's very experimental. And using IPython widgets, you can, for example, see the results of changing the threshold of an image. So it's also a way to test very easily and fast the output of a function. So I just have to apologize because this is something I copied and pasted from the web. Yesterday I tried to run IPyWidgets on my notebook, but I couldn't make it working. So, who's using IPyWidgets here? Some people. Okay. So maybe someone will help me after to make iFi widgets work on on my notebook. But so for so in order to explore data and to have an interactive workflow, it can sometimes be problematic if you have very large data. Because let's say my tomography images, there are 1,000 cube for just one image, and sometimes I have hundreds of them. And I want to explore the result of several filters, several operations that I will combine. Like here, for this tomography image, I want to segment 3 phases. So I will do a first threshold, a median filter, second threshold, some mathematical morphology. And each of these operations will take from a few seconds to 1 minute. And it's very frustrating to start again the whole pipeline every time you want to change just one parameter in the filters. So this is where we have great tools like JobLib with its memory function, because you can just cache the output of some functions, and then when you change something in your program, if other variables were not changed, then the computations will not be done again. So it's a way, first, of course, to make things faster, work faster, but also to increase interactivity and how you, the easiness with which you will explore your data. And last but not least, something which is really great for learning is going to conferences. So congratulations to all of you. I think you found the best way of learning. So you learn at tutorials, during talks. Yesterday at the pub, I was learning about great ways of web scraping from Alex, for example. So it's really a way to discover new things, don't stay in your energy minimum, meet new people. And I've taken part in the organization of EuroSciPy conferences for some years now. So Alex already said that next year it will be in Trento. And so one output of this EuroSciPy conferences is the SciPy lecture notes website. So who knows about the SciPy lecture notes? Not many people. This is interesting because it's an umbrella project for a lot of tutorials. You have several weeks of tutorials. So if you just Google SciPy lecture notes, you will find very easily. And it has several chapters. One is for beginners, so really the core of scientific Python. Advanced chapter is about learning more tricks, and some package-specific chapters as well. So it has been curated and enriched over the years, even if we were still looking for people to help along maintaining and contributing new chapters. We would really need a pandas chapter, for example, for the beginners part. So it's also a way to make sure that people can learn easily, because when you give tutorials or trainings to 20 people, it takes a lot of time and energy. But when I have a new person coming to my lab, I usually tell her, oh, just go to the SciPy lecture notes and read the intro chapter. And so that after the person can follow maybe directly an advanced training and not spend too much time on the intro part. So one very last thing before taking questions. In my abstract, I said that the scientific Python ecosystem is a great way to learn programming fast, but it's also a great way to learn science. And I think, for example, scikit-learn has been a real game changer so that people would learn machine learning. So obviously scikit-learn empowers people to do some machine learning, but it also teaches them how machine learning works. And like this gallery example about underfitting versus overfitting, it's really something that you could find in a statistics book or in a regular university class. So that's why scikit-learn is also a great tool. And we have the same in scikit-image. Like, for example, if you want to learn what is picture denoising, comparing different denoising filters is a good way to get some intuition about how these different filters work, like total variation, wavelet denoising, and so on. And in the documentation, we also have some quite mathematical explanations so that you can, of course, just compare the output of filters and use them without understanding really what's going on. But if you want to go further, there is food for thought and for learning more the mathematics background. And here is an example from my research where we have this noisy image and we can use several denoising filters from very basic ones like the median filter to the total variation filter, which gives the output is posterized image, so images with constant gray levels, and you see how the histogram is improved from the original image where you have this big, we say potato in French without any peaks, to an histogram where you have two really well-defined peaks and the total variation is really the best filter. So it's a kind of thing that you can test quite easily with the gallery examples and their explanations. And so this will be my final slide. I would say that so really the best way of learning is contributing to open source because it really boosts your learning pace. So for me, starting contributing to scikit-image, I learned a lot about programming because when I started, I didn't know much about version control, about testing and so on. So I learned all this machinery of maintaining a package. But I learned also a lot of image processing, which was, I considered it as my strength when I joined the team. But I learned so much just talking with the other developers, like the discussions we have about state-of-the-art algorithms on the GitHub, like this snakes algorithm for segmentation. It taught me really a lot of things. So I would say that being a contributor is like the ultimate way of learning about both programming and science. So I had a few slides about performance and so on, but it's more if you have questions. So to wrap up, I think when you're giving a keynote, you have this reaction, oh, what should I be talking about? Is it like important stuff, like where do we come from, what are we, where are we going, which is the title of this beautiful Gauguin painting. So for me, the interest of this talk was more to see what is great with our tools, what can we learn about them to create new tools, especially how to empower people to learn fast our tools and how to use them, and maybe do we need also other tools. So I think we all know that we've got great tools, but can we make them even more self-learning, making the documentation more interactive, for example? And for this, we need your ideas, but also your contributions to the ecosystem. And you don't have to be a programming genius to be a contributor, even a co-contributor. I'm certainly not a programming genius, but if you just have ideas about what users think, how they learn, and you can make very useful contributions. Thank you.
Thank you. That was another great keynote. On the topic of contributing to open source, just a reminder that we have the Panda Sprint coming up after the coffee break. Is Mark in the room? Not yet? Can't see him. Maybe he's already there. Anyway, the Panda Sprint will be in the Mortimer room at the end of the floor. Do we have a mic for the audience? Is there any question? Time for one question or two? There's a question here, please.
How do you relate to the OpenCV community, or if at all, in terms of, do you have any kind of knowledge transfer between how the libraries are kind of structured?
Thank you for your question. It's an important question. So OpenCV, for those who don't know, OpenCV is a computer vision package, and it's really popular. We don't interact much. I think some of our developers are using OpenCV as well, so it makes sure that we know what's inside OpenCV, but we don't work with the development team of OpenCV. Maybe we should, actually. I must say that your question triggers other questions for me, like should we work with them? We have slightly different goals because we're not a computer vision package. We have some functions like for feature extraction, for simple registration, but we don't target exactly the same users. But I would say it's even more a reason to work together and to see if there are some possible interactions. The thing is that OpenCV is developed mostly, I think it's C++, yeah, and so Python is it's mostly bindings and API, but they've made real progresses about this. When we started working on scikit-image, it was not possible yet to have NumPy arrays as arguments of OpenCV Python bindings. Now it works really well. But I don't know if they have a strong Python team, but I should definitely ask. Thank you for your question. Yeah.
Thank you. Yeah, just before the break, one last announcement. Gina from NumFOCUS is looking for a first-time attendee, somebody who is here for the first time. For an interview, short interview. The question will be, what motivates you to be here so early in the morning? Look for Gina next to the registration desk. Now we have a coffee break, and let's thank Emmanuelle one more time.